Very good morning to all present here. I am Dr.M.Mlarvizhi. I am working as an assistant professor in Department of Physics, K.S.Rangasamy College of Technology, Tirchangur, Namakkal District, Tamil Nadu. Today we will see the topic crystal structure of solids. This topic coming under the model 1 of the paper Physics for Electrical Engineering. So first we will see the introduction. What is matter? Matter is anything that has mass and takes up space. It exists in 3 different states. I hope you all know very well about the different states of matter. These are solid, liquid and gas. All the materials are composed of atoms and molecules. It consists difference in interatomic distances. Solid material consists less interatomic distance than the liquid, and liquid consists less interatomic distance than the gas materials. Out of these 3 different states of matter, now we will see the solid materials. Solid is essentially an ordered array of atoms bound together by electric forces to form a very large molecule. So what are the classification of solid materials? Crystalline, polycrystalline and amorphous. So next we will see what is crystal physics and crystallography. Crystal physics is a branch of physics that deals with the study of all possible types of crystals and the physical properties of crystalline solids by the determination of their actual structure by using X-rays, neutron beams and electron beams. Suppose if you are using X-rays with the wavelength of 10⁻12 to 10⁻10 meter, we can use X-rays to predict the structure of the particular solid material. These X-rays consist interatomic distances equal to that of a solid material. Diffraction can easily occur when they are passed through the crystals. So, in a crystal, atoms are arranged into a regular periodical repeated structure that extends throughout the whole sample. It has directional properties and therefore called as anisotropic substance. So, crystals are called as anisotropic substance due to its long periodic array. The atoms are said to have long range order. Polycrystalline material is composed of many small crystals or grains of somewhat irregular size. In an amorphous solid, a long range order is absent. We have short range order. So this is a structure of crystalline material and polycrystalline and amorphous. So what is crystalline material? Is one in which the atoms are situated in a repeating or periodic array over large atomic distance, that is long range. The examples of crystalline materials are metallic crystals and non-metallic crystals. So what are the elements coming under metallic crystals? Are copper, silver, aluminium and magnesium, etc. The non-metallic crystals examples are carbon, silicon and germanium. Non-crystalline solid materials, there is a lacking of systematic and regular arrangement of atoms or ions over relatively large distances on an atomic scale. It consists only short range order. The examples are glass, plastics and rubber. So next we will see what are the differences between amorphous and crystalline materials. In amorphous, there is an irregular pattern of ions, molecules and atoms in a solid. It melts over a range of temperature. There is no definite heat fusion. Examples include glass. So amorphous called as isotropic. So the crystalline materials consist of regular repeating arrangement of components in a solid. It has a short melting point. It consists of definite heat fusion. Examples are including diamond. So the crystalline materials are called as anisotropic. These are all the comparison in between amorphous and crystalline materials. So next one, what is space lattice? Space lattice, we can call it as a crystal lattice also. It is a three-dimensional collection of points in space. The environment about any particular point is in every way the same. It is 3D array of points coinciding with atom positions. So unit cell is the basic structural unit or building block of the crystal structure, and it defines the crystal structure by virtue of its geometry and atom positions within. Once again I will repeat it. What is unit cell? Unit cell is a basic structural unit, okay, or building block of the crystal structure, and it defines the crystal structure. Once again it defines the crystal structure only by virtue of its geometry and atomic positions. So, concludingly, what is a crystal structure formula? There is a formula for crystal structure that is equal to space lattice plus basis. The concept of crystal system is used to classify crystal structures on the basis of unit cell geometry, that is unit cell edge lengths and interaxial angles. The unit cell geometry is completely defined in terms of 6 parameters: the 3 edge lengths A, B, C, and the 3 interaxial angles alpha, beta, gamma. So what are the types of crystal structures? There are 7 crystal structures are there: cubic, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral, and hexagonal. The lattice parameters involving different types of crystal structures are: for cubic, the 3 interaxial lengths A, B, Z are equal. Interaxial angles alpha, beta, gamma are also equal to 90 degree. This is a unit cell geometry of the unit cell, that is the 3 axial lengths are equal and the 3 axial angles are also equal to 90 degree. Likewise, the tetragonal consists of interaxial lengths A and B are equal, they are not equal to C. Then alpha, beta, gamma are also equal to 90 like the cubic crystals. What about orthorhombic case? The interaxial lengths A, B and C are not equal with each other, then alpha, beta, gamma are also equal to 90. Monoclinic, all the 3 interaxial lengths are not equal to each other, and also interaction angles alpha, beta is equal to 90, gamma is not equal to 90. For triclinic, the 3 interaxial lengths are not equal to each other, and also alpha is not equal to beta and not equal to gamma, that is also not equal to 90 degree. Rhombohedral, it can also called as a trigonal. In this case, all the 3 interaxial lengths are equal, alpha and beta are equal but not equal to 90 degree. All the 3 interaxial angles are equal but not equal to 90 degree. In the case of hexagonal, A and B equal, not equal to C, and alpha and beta are equal to 90, gamma is equal to 120. These are all the lattice parameters and unit cell geometry of the 7 crystal structure. Next to 7 crystal structure, there is a 14 various lattices. Okay, there is a various lattice positions are simple, base centered, body centered, and face centered. With these all 4 various lattice, we can various classified the 7 crystal systems, we can get the 14 various lattices. For cubic, the various lattice are simple, body centered, and face centered. Characteristic symmetry elements for cubic are 4 3-fold rotation axes along cube diagonal. The examples for cubic system are sodium chloride, calcium chloride, and NaClO3. For tetragonal, the various lattice are simple and body centered only. The characteristic symmetry elements are 1 4-fold rotation axis. The examples are NaSO4, SnO2, indium white tin. Orthorhombic, there is a possibility of 4 various lattice: simple, base centered, body centered, and face centered. The characteristic symmetry elements are 3 mutually orthogonal 2-fold rotation axis. For monoclinic, there is only 2 various lattices are available: simple, base centered. There is a characterization of this various lattice at 1 2-fold rotation axis. For triclinic, the various lattice is only one is available, that is simple. there is no characteristic rotation. For trigonal, there is also only one radius lattice, that is simple. There is a one-pole rotation axis is available. For hexagonal, there is also only one radius lattice, that is simple. There is also a one-pole rotation axis is available. Okay, the possible examples are here. In this video, we covered what is matter, what are the different types of states of matter, what is crystal, what are the types of crystalline materials, what is phase lattice, then what are the types of crystal structure and their lattice parameters. With the lattice positions, Gravius provided 14 types of Gravius lattices. We also covered Gravius lattice also. In the next video, we will see what is the special characteristics of all the crystal systems. Thank you.